So today we're going to try and answer this exam question, which is explain why reactivity of elements increases with further down group 1. Now to do this we need to revise 4 things. One is electron structure, periodic table, ion formation and also electrostatic forces. So let's have a look at the electronic structure first. This diagram shows the electronic structure of the first 18 elements found in the periodic table. And we're looking at a couple of patterns from this diagram. So going down the periodic table, you should notice that the number of electron shells increases as you go down each row, as you're going down each period of the periodic table. The second pattern to notice is one that's going across the periodic table. So as you go from the left-hand side to the right-hand side. Now what you should notice here is the number of electrons that you found in the outer shell increases by 1 as you go across. So if you look at the middle row where we've got lithium on the left-hand side there, you've got 1 electron in its outer shell. Move along one into group 2 and you've got beryllium with 2 electrons in its outer shell. In group 3 you've got boron, which has got 3 electrons in its outer shell, and you carry on all the way up until you get to neon, which has got 8 electrons in its outer shell. It's got a full outer shell, so they increase as you go that way. Now the periodic table, the elements are always laid out in order of atomic number. Those elements with similar properties form columns known as groups. Now the group number tells you how many electrons are in the outer shell. That's one thing that is important to take away from this. And then the second important thing is that the rows are called periods, and each period represents another shell of electrons. So carbon is in period 2 and group 4. So because it's in period 2, it's got 2 electron shells. The first one is a full shell of 2 electrons, and the second shell, you know that it's got 4 electrons in it because carbon is found in group 4. Okay, so in total, carbon's got 6 electrons. Now, how many electrons does beryllium have in its outer shell? If you looked at a periodic table, beryllium is in group 2, so it has got 2 electrons in its outer shell. How many electron shells does calcium have? Well, calcium is found in period 4 of the periodic table, so it's going to have 4 electron shells. Okay, you're going to have a go at doing this now. So how many electron shells and how many outer shell electrons do these 3 elements have? So magnesium, nitrogen and rubidium. Now one thing I want you to notice is don't miss the first period is that really small one at the top with hydrogen and helium in it. That's period number 1. The second period starts with lithium on the left hand side, the third period with sodium on the right hand side, fourth period with potassium, and so on. Okay, so pause the video now and have a go at answering those questions for me. Okay, let's see how you did. So can you grab a different coloured pen for me? And we're gonna mark these now. So magnesium, it is in group 2 and it is in period number 3. So because it's in period number 3, it's got 3 shells. Group 2 tells you it's got 2 outer electrons. Nitrogen is in period 2 and group 5, so it's got 2 shells and 5 outer electrons. And then rubidium is in period 5 and it is in group 1, so it's got 5 shells and it's got 1 outer electron. Now, forming ions. So an atom always has the same number of electrons as protons. That's what makes it a neutral overall charge. Okay, so there's no charge in an atom because it's got the same number of electrons as protons. Now, an ion is formed when an atom either loses or gains extra electrons. So it's either going to lose negative charge or it's going to gain negative charge. This means your ions always have a charge on them. They are charged particles. Let's step back a minute. So we're going to look at neon. There it is. It's a noble gas and it's got a full outer shell of electrons, which makes it inert. Okay, so it's unreactive. That's what that word inert means. Now, other elements, they want the same electronic structure of the noble gases. So they want full outer shell of electrons. Now, this is the electronic structure of fluorine, which is a very reactive element, and we're going to compare that with neon, which is our unreactive noble gas. So fluorine has got 7 electrons in the outer shell, whereas neon has got 8 electrons in the outer shell. It's got a full outer shell. Now, fluorine wants to be just like neon. It wants the same number of electrons as neon. It wants that full outer shell. Okay, so how is it going to do this? So what happens if we add 1 electron to fluorine? So there we go. We're going to put an extra electron onto the outer shell of fluorine, and all of a sudden, fluorine gets the same electronic structure as neon. Okay, now all elements want to do this. This is what makes elements reactive. Okay, they are trying to get that full outer shell. Okay, so electrons are negative. They've got a charge of -1. So if we were to add an extra -1 onto fluorine, that's in effect what we're doing. It's going to change the charge on our atom. It's going to give our atom a -1 charge. So not going to call it an atom anymore. We're going to call it an ion because it's got a charge on it. And to show that we've got an ion there, we put 2 square brackets around it and we put a little negative charge at the top right-hand corner. So that is your electronic structure of your fluorine ion. Okay, that's how you draw it. Now, a similar sort of thing can happen with sodium, which is a very reactive metal. I'm going to compare this to neon, which is our noble gas, on our reactive noble gas. Now, sodium's got 1 electron in its outer shell, and neon has got 8 electrons in its outer shell. Now, sodium, again, it wants that same electronic structure as noble gases. In this case, it wants the same electronic structure as neon. How can it easily do this? Okay, well, it can do it by losing that outer shell electron. So that outer shell electron disappears, and then sodium now gets the same electronic structure as neon. Now, if we're taking away 1 negative charge, okay, it leaves us with an overall positive charge on our sodium ion. So to indicate this, put the square brackets around it, and you put a little plus at the top right hand corner there. So now you know that the sodium ion has got a positive charge of +1. Now, if you were to add 2 electrons to an atom, or you take 2 electrons away from an atom to form its ion, then you obviously then need a 2- charge or a 2+ charge, depending on what you do. So you need to just think about how many electrons you are adding and taking away from your atom when you are forming your ion. Okay, but the idea is that they always want that full outer shell. So, second task for me, you're going to draw me the electronic structure of a potassium ion, and then I want you to draw me the electronic structure of an oxygen ion, please. So pause the video now and have a go at doing that. Okay, so hopefully what you should have drawn was that for your potassium ion. So you've taken away that outer shell electron and you've turned it into a positive potassium ion with a charge of +1. Now your oxygen, to get your full outer shell on your oxygen, you need to add 2 electrons. So you should have added 2 electrons to it. And because you're adding 2 electrons in this case, you get a 2- charge on your oxygen ion. So what has this got to do with reactivity? So the more easily an atom loses or gains an electron, the more reactive it is. So I want you to watch this quick video clip on the reactivity of group 1 metals.
Now let's see another reaction of the alkaline metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkaline metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
Okay, so as we're looking at group 1, all the elements in the group have got one electron in their outer shell. They all want to lose that electron so they get their outer shell, that full outer shell electronic structure. So from the video, hopefully you saw that there's the trend in reactivity as you go down the group. So you've got lithium going all the way down to cesium as far as we went, and you should see that the lithium is the least reactive and at the top, and as you get down to cesium and francium at the bottom, that is the most reactive. So reactivity increases as you go down the group. So that means that electrons are more easily lost as you go down the group. So cesium can lose its outer shell electron more easily than what rubidium can, which can lose its outer shell electron more easily than what potassium can, which can lose its outer shell electron more easily than what sodium can, which can lose its outer shell electron more easily than what lithium can. Okay, so as you go down the group, you've got to think of cesium can lose its electron more easily than what lithium can at the top. So why is this the case? So nucleuses are positive, electrons are negative. We know this, okay? Now, opposite charges are attracted to each other. So this is called the electrostatic force. So your electrons are attracted to your nucleus, which is positive. So your electron's negative, nucleus is positive. They are attracted to each other by what is known as an electrostatic force. Now, the further objects are away from each other, the weaker that electrostatic force is. So I've got my positive nucleus there, and I've got my first inner shell of electrons. Now I want you to imagine that shell is full. So I'm going to add my next shell, and I'm going to put one electron on it. So that's lithium. Okay, so lithium's outer shell electron is there. You can see it's a little distance away from the nucleus. Now I want you to try and imagine that now that shell becomes full, and I get to my next element going down the periodic table is sodium. And sodium's outer shell electron, can you see that it is further away from the nucleus than what lithium's outer shell electron is? Okay, so because it's further away, those electrostatic forces from that outer shell electron to that positive nucleus are getting weaker. Let's carry on. So there's potassium. Its outer shell electron is even further away from the nucleus, and those electrostatic forces are getting even weaker. And then we carry on to rubidium, which is still further away, and then cesium, which is a long way away from the nucleus compared to lithium, which is really close. So you can see that those electrostatic forces holding that outer shell electron in cesium must be a lot weaker than the electrostatic forces holding the outer shell electron of lithium into its nucleus. So cesium can more easily lose its electron than what lithium can, just because the distance from that outer shell electron to the nucleus is much bigger. So as you go down the group, the outer shell electrons get further away from the nucleus. That means the electrostatic forces are weaker, and then the outer shell electron is easier to lose the further away from the nucleus you are. And that's what makes the element more reactive. That's why cesium is more reactive than lithium. because its outer shell electron is further away from a nucleus than what lithium's is. Okay, right. Multiple choice task for me for task number 3. Read through those questions and then just write down, in each case, is the answer A, sodium, or B, cesium. Pause the video now and have a go at that for me. Okay, so looking at the periodic table, which element has the greatest distance between the nucleus and the outer shell electrons? It's got to be cesium. Which element will have the weakest electrostatic forces between its nucleus and its outer shell of electrons? It's got to be cesium. And then which element will lose its outer shell electron more easily? Again, it's got to be cesium. Okay. Right, back to the exam question then. So the last thing for me today. Explain why the reactivity of elements increases the further down group 1 you go. So things you need to be thinking of here is how easily is it going to lose an electron? The distance between the outer shell electron and the nucleus. Okay. What type of forces are they described as? You need to try and incorporate all that into a written piece for me. So it's worth it's worth 4 marks. So once you've done this is the last task for today. You can pause the video now, have a go at answering this question for me. You should have all the information from everything we've done so far today. And then if you can submit everything for me via Teams. Okay, thank you very much, and I'll speak to you again soon.